Today we're going to do Unit 1, Lesson 3. We're going to look at some diagrams. So you're going to represent atoms in different ways. The protons, electrons, neutrons is what's going to help you be successful at this. This is really important for the rest of this year, especially this unit for sure. If you know how to draw these, it's going to help you draw the more complex molecules and the compounds when you get to that stage. All right. So, Bohr diagrams, I kind of showed you a little bit what it would kind of look like. We're not going to take shortcuts today. We're actually going to do this full-on scale kind of thing. So, here we go. Use Bohr diagrams. So when you talk about Bohr diagrams, you can use the atomic number and the mass number. And of course, we're going to subtract those two to figure out how many neutrons we have. So we're going to put the protons and the neutrons in the nucleus, and we're going to put the electrons and the appropriate energy levels around it. Apparently some of you guys have done this before. So it's maybe a review for you. Hydrogen. So, hydrogen is atomic number 1, so that's 1 proton. It has a mass of 1, so that means the 1 proton is the mass of hydrogen. So we don't have any neutrons in this case. You can either, if you want, you can put 0 neutrons. You don't have to. It's up to you. Hydrogen's got 1 proton. That's the nucleus right there. If you want to use different colors and you want to be all pretty, feel free. If it's got 1 proton and we're just drawing neutral atoms today, how many electrons does it need? 1. Anyone? Sure. 1. We're going to use a dot to represent an electron. Okay? How many electrons can go on the first energy level again? 2. Yeah, sure. Alright, so here we go. That's what hydrogen looks like. That's called the Bohr diagram. Nitrogen. We talked a little bit about this at the beginning of the year. These are nice, simple diagrams. They're easy to represent. It's not that cloud thing that we're talking about, the quantum mechanics model. It's nice and easy. Electrons go on a specific energy level, even though this is probably not what it looks like, right? Nitrogen is number, what, 7, right? So we've got 7 protons. It's got a weight of 14.01, so rounded, that's 14. So if the weight's 14, we've got 7 protons, we need 7 jimmies, right? 7 Jimmy neutrons. That's funny. Laugh. If you're listening to this on the internet, laugh. 14. We need 7 electrons, right? 7 positive, 7 negative. So you said that 2 can go in the first one. We're going to learn that electrons, after a certain time, they want to pair up. It's something called VSEPR, or valence shell electron pair repulsion theory, which will be about lesson 10 for you guys. They have this unique ability to pair up. So right now, we're going to put 1 here, and the other one's going to go right beside it. They're going to pair up. All right? The next energy level can hold how many could I put in here if I had to? How many could I put? 8. So you can put 8 in here. We don't need 8, of course. If we put 8, there's too many. We need another, what, 5, yes? We got 2 in the first one, so we need another 5. Here's how they fill up, okay? You'll learn this in grade 13. You don't need to know this now, and I'm going to talk about S, P, F, and D and stuff. But grade 13 is university, by the way. We're not there. We're in grade 11. We're okay. There's little suborbitals in these orbitals here. So in these shells, basically, and usually refer to them as S, P, F, and D. And there's many different ones and stuff like that. You don't need to worry about that. What I'm going to tell you is that there is suborbitals in here. They try to take positions. In other words, they fill up even on a suborbital level. They fill up one at a time, kind of thing. So basically, you have to know that there's possibly 4, and this is how they kind of get filled up. 1, 2, 3, 4. So they try to take positions as far apart as possible. Firstly, okay. That's the first thing that's going to happen. After this, you don't have a choice. There is only 4 in this one, and like I said, you don't need to know that. You're just going to start at the top and work your way around. 12, 3, 6, 9. That's all you need to worry about. Okay. After this, you don't have a choice anymore. They have to start to pair up. Okay. So if you can have 8, you can think about 4 positions. 1, 2, 3, 4, and then the 5th one has to go back up at the top, and they have to start to pair up. Okay. And that's a little bit about VSEPR, valence shell electron pair repulsion theory, and like I said, other stuff as well. Basically, you just have to know how to draw these, okay, is what I'm trying to tell you. Sulfur, we got 16, it's number 16, so we got 16 protons. We have 32.07 for the weight, so we're going to round that to 32. We're going to get 16 neutrons. We're drawing the most common isotope. Remember that term from last day? Common isotope. It's the one that's on the periodic table. That's the one we're drawing. Nucleus, okay. First energy level can hold 2, 1, 2. Second energy level can hold 8. We're going to need all 8. And technically, this is how they get filled up first, all right? You don't have to draw it like this. If you want to say, well, it's got 8, I need 8, draw them, whatever. I don't care. But technically, this is how they fill up. 1, 2, 3, 4. After that, I know I'm out of spaces. I'm out of suborbitals, whatever kind of thing. I need to start doubling them up. 5, 6, 7, 8. All right? So that's a total of 10 we have so far. And then finally, the last one, of course, we'll need 6. 1, 2, 3, 4. I guess I should have asked you, how many can you have in that third energy level? You can have 8, right? We only need 6. So 1, 2, 3, 4, 5, doubling up, 6. Okay? So 2, 8, and 6 is 16. If you don't believe me, get a calculator and figure that out. Okay. And finally, aluminum. 13 protons, 26.98. So we'll round that one up to 27, of course. That's a way to 27 there. We need 2. We need 1, 2, 3, 4, 5, 6, 7, 8. That's a total of 10. Well, we need 3 more. Okay. 1, 2, 3. Okay. And we'll stop there. Any questions? Anyone? Feel free to ask. Don't worry, the microphone doesn't even pick you up. Okay. So if you're listening and you ask a question, you won't even hear yourself. So don't worry. Questions? Now, you might say, well, what if I don't draw it like this exactly? You should, and there's a reason. Trust me. When we get to the drawing stuff, it's going to help you out immensely. All right. Whatever you do, don't pair up. There's 3 here. Don't put 2 together and then 1 over here by itself, because that's not what it looks like, and that's going to create problems later on. Okay? Always separately first, and then you can start filling them in after. Yep. Patience. Lesson 10, or maybe 11. All right. So you want to keep them separate because, you know, when you look at the periodic table, take a look at the periodic. You should have your periodic tables though. Take a look at the periodic table. We're going to review this tomorrow anyway, but when you look at aluminum, okay, number 13, right? Look up here. Aluminum has how many valence electrons? That's another term you should know by now. What's valence electrons again? Not you, somebody else. I'm going to pick on somebody. Sure. Right, the electrons on the most outside energy level, right? Or the outside electrons. So there's how many here? 1, 2, 3, right? Those are the valence electrons of aluminum. Now, why do you draw them? Well, kind of why do you draw them separately, but why are they out there? Remember, if aluminum can get rid of 3 electrons, look, 1, 2, 3. If it can get rid of those electrons, what's on the outside energy level now? It's now what? Got how many? 8, right? So it makes it more stable, right? So why does aluminum form a 3 plus charge? Because it wants to get rid of 3 electrons if it can, right? Look, it's more stable now, right? So we want to make sure we represent that accurately. And when we get to, for example, nitrogen, you know, look at nitrogen here. Is it going to get rid of 5 electrons on the outside energy level? Look where nitrogen is. What's more easier? What's easier for it? It wants to gain 3. Because look, if it gains 3, 1, 2, 3, right? If we fill those 3 in, where are those electrons coming from? Somewhere else, probably a metal in most cases. But if we can fill those 3 in, now it's more stable, right? It has a full outside shell again. That's what all bonding is related on. Whether it's molecular or ionic, which we'll start tomorrow, okay? It's all based on that. It wants to become more stable if it can, okay? Now, can you find nitrogen by itself? Well, actually, technically, you'll find it in 2s usually. And I'll show you that, why that is. But what's important here is that you got 3 electrons by themselves because it wants to gain 3. That's why it forms a 3- charge, which is not on your periodic table, which we'll talk about, okay? So I'm just going to get rid of this for a second here. I just want to draw them again here, just in case somebody's not sure here. That's what nitrogen should look like, of course, and aluminum should look like that there. Okay, good? And we'll get into that. Okay, we will. That's part of the naming thing and all that other stuff we're going to do. Patience. Electron energy level diagram is next. Electron energy level diagrams are basically working like a Bohr diagram. You start on the inside and you work way out. And I don't know if you've done these before or not, but basically it is what it is. It sounds like it is. Energy level diagram. So it's levels. Okay, you're going to start with the symbol down here. So symbol. You're going to do the, leave yourself some room because you're going to go up. Okay, so symbol, 1 proton, no neutrons. If you want to put that in, you can. It's got 1 electron. Okay. So that's what hydrogen would look like as a electron energy level diagram. Might be a little easier for nitrogen. Nitrogen, 7 protons, 7 neutrons. Okay. 7 protons, 7 neutrons. It's got 2 electrons in the first energy level, just like we drew before. 2, and then another 5. So we'd write it like that. Okay. And you'd basically just keep filling in energy. As you work your way out, you're filling in the levels. Okay. Sulfur, 16 protons, 16 neutrons. You got 2 in the first energy level, 8, and then another 6. All right. So symbol, nucleus, first ring, second ring, third ring. Oh, I forgot my joke too. All right, we'll come back to that. Aluminum. Number 13, right? So we talked about this on the last one, 13 protons. It's got 14 neutrons, okay? 2, 8, and it's got 3 in the outside energy level. If you're thinking about valence electrons only, of course, you can just look at the top one there. Well, hydrogen's got 1 valence electron, nitrogen's got 5, sulfur's got 6, aluminum's got 3. While I'm on that topic, I guess we better come over here for a sec. So let's look at the periodic table. Those people at home cannot see this. That's why it's good to show up the class. When we talk about valence electrons, which is actually going to be our next one here, when you think about it, nitrogen, how many valence electrons is nitrogen? Well, it's got 5. How did I know that? Well, I went through the whole process, right? I said, well, look, here's nitrogen. It's number 7, 7 protons, 7 electrons. 2 go in the first one, 5 go in the second one. Remember, the first energy, where is nitrogen located? It's located in the second period. So if you look at just this energy level, the second energy level, that's the only one you really need to worry about because the first one's filled, obviously, right? Nitrogen's not going to look like helium at any time because it would have to lose, well, quite a few electrons for that to happen. Nitrogen's going to become more like neon, if anything, right? It's in the second period there. The first energy level's filled. It's got 2 electrons in there. So how do you know how many valence electrons you have? Look, 1, 2, 3, 4, 5. It's got 5 valence electrons because it's the 5th one over, right? How many valence electrons does neon have? Neon is stable. It should have 8, right? Look, it's the 8th one over. 1, 2, 3, 4, 5, 6, 7, 8. And if you want to think of it this way, right? 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. Those are the first 4. Then they start to double up, right? So first one that doubles up, that's the 12, the 3, the 6, and the 9 again, right? They doubled up again. So if you just count from left to right, that's going to be your valence electrons. That's going to help you with the next thing here, by the way. What about calcium? How many valence electrons does calcium have? 2. It's the second one over. What about strontium? 2, right? Why are they 2? Well, look, they're in group 2. They have 2 valence electrons, right? That's why they're in that group, because they all behave similar. They all have 2 electrons they wish to get rid of. So it leads to similar properties. Just like group 1 all leads to similar properties. Okay? We looked at today in the lab, lithium, sodium, potassium, rubidium, cesium, francium. They all have 1 that they want to get rid of, right? Now, the thing that you have to be careful of is when you get to here. Scandium over, right? In this section here, 3 to 12, the transition metals are multivalent, okay? And that no longer applies. So one of the things you have to keep in mind here, if you start counting over here, it's I'm going to ask you this question at some point in time, and we'll do this. Patience, all right? But look, 1, 2, 3, 4, 5, 6, 7, 8. Does that mean iron's stable? No, because this is the university part of this class, right, that we're not going to talk about. So it doesn't mean you would draw 8 electrons around. It doesn't apply anymore. Okay, it only works for these first, well, basically period 3 and up, and then these ones here kind of thing. It also kind of works for some of these over here, and we'll talk about that later on, right? But the 3 to 12 part is different, all right? That's more complex. I'll show you how to draw those. So you can't just count over. So in other words, for example, if you went to cobalt, you'd have 9. How am I going to fit 9? I've never heard of that before. 9 electrons in an energy level kind of thing. It's not going to happen. Okay, so there's different ways of representing that, and then, like I said, we're not going to worry about that here. Okay. If you really want to know, stick around. I'll kind of allude to a little bit, and if not, then go to university, I guess. Lewis diagram's last one. I kind of led you into this kind of thing. Lewis diagram includes a symbol and only the number of valence electrons. That is it. There is no protons, there's no neutrons, there's no rings, there's nothing else. You guys have probably done this one before, yes? No, okay, that's okay. I assume that you haven't, so don't worry. Anything that you're going to need, I'm going to tell you, okay? Lewis diagrams, also know this. Lewis diagrams are also called electron dot diagrams. Same thing, okay, because really you're using electrons as dots, but you'll hear both terms, okay? So make sure you know that they're the same thing. Lewis diagrams are electron dot diagrams. Hydrogen symbol, and only the valence electrons. So in this case, hydrogen has 1, yes? So we need 1 dot. We're going to put it right there. Okay? I'll show you a few more, and then we'll talk about stuff. Okay? Nitrogen. Okay? Nitrogen has how many valence electrons? Well, we talked about it, right? Look, first energy level, where's nitrogen? It's in the second period. First energy level is filled. That's the first 2. We need another 5. 1, 2, 3, 4, 5. So we need 5 around here. How are you going to fill them in? Just exactly like a Bohr diagram. 1, 2, 3, 4. After they take those positions, they have to start doubling up or pairing up. Electron pair repulsion. Okay? So the 5th one goes there. Okay? If you draw, this is crucial for the rest of this unit here, I'm telling you. I'll say this probably 1,500 times. By the end of next week, you're going to be like, everything's apparently crucial in this class. But it is, because it's going to help you draw the other structures. It's going to lend itself. What kind of shape is that probably going to form? Trigonal pyramidal, probably. You're going to know that. Bond angle. Boom. 107.3. Right. Sulfur. Sulfur's got, well, let's see. 1, first energy level is filled, second energy level is filled. Sulfur's in the 3rd one. So 1, 2, 3, 4, 5, 6. 6. Okay? Sulfur usually, if it's the middle atom, lends itself to a bent shape. Okay? Aluminum, last one here. 1, 2, 3. Okay? It's got 3 valence electrons. 1, 2, 3. It's the 3rd one over. Remember, it's the number of protons, but it has to equal the number of electrons. So when we're talking about electrons, we're talking about kind of protons in the same way. These are neutral atoms, of course. All right? Is that good? Questions, anyone? How are you going to remember these? Well, Lewis diagrams, electron dot diagrams, you're going to have the symbol and the dots. Energy levels, right? Electron energy level looks like levels, basically. Stairs, kind of like, right? Levels. And my favorite, Bohr diagrams have rings around them, which makes them Bohr ring. Bohr ring. Get it? Okay. Rings, and the guy's name's Bohr. Not everyone's I'm just explaining this to you. Bohr ring. Okay. Homework. There you go. I usually don't spend a lot of time on homework here because it's pretty self-explanatory for the most part. But hey, real quick here. The first one, you just got to tell me how many protons, electrons, neutrons. You don't have to draw me anything. Just a little bit of review. What are these numbers out in front here? What are those for? What do you think? Look at your periodic table. Anyone? Yeah. The what, sorry? Yeah, the mass. Okay, so that's the mass I want you to use. If you look up bromine, remember all bromines have 35 protons. That's never going to change. That's atomic number 35. That's what makes bromine. Trying to talk real fast. Now, that's not going to change. What changes, of course, is the neutrons, perhaps. Now, when you look up bromine, it's 79.90, which is this one here, yes? This is, what are those called? Yeah. Isotopes. So this happens to be the most common isotope that we know of bromine. It's the one on your periodic table. There is other isotopes of bromine, okay? For example, when you get down to iodine here, that mass does not match up with the one that's on the periodic table. I want you to use this mass, okay? The 123, not the one that's on your periodic table. So you need to adjust that accordingly. Different number of neutrons, okay? Here, you're going to draw, there's not going to be enough room for you guys, so you might have to do this in the back or something. But hydrogen, I want a Bohr diagram of hydrogen. This hydrogen's a little bit different. This one actually has a neutron in it, right? Because hydrogen's one proton. In this case, if it has a weight of 2, it needs a neutron. So there is hydrogens that have a neutron in them. It's not the most common one, but there is such a thing, okay? And then so on and so on. There's electron energy diagram, and of course Lewis diagrams. So go ahead and you can work on those. If you have any questions, obviously let me know. Okay.